All right. Let's keep going when we were talking about primitive types last time. So again, kind of remember this slide. We're walking through history a little bit here. Um, really, right now we're living over on this side of things, our strongly typed languages compared to loosely typed languages, but don't necessarily make that big of a deal. It ultimately comes down to when you create a variable. Maybe it's your age. In a strongly typed language, you would say int age equals 21. In a loosely typed language, you would say age equals 21. Just the difference between whether you say what kind of thing you're going to put in there or you just put it in there. Um, an advertisement for loosely typed languages might be, oh, well, you can create a variable like age and you could put a number in there 1 second. And then 20 minutes later, you could put a string in that variable if you wanted. You could store, you could say age equals Mike. But that doesn't make sense. Usually you want to have variables that have meaningful names based on the values that are stored in there. So there isn't that big of a difference between those two from a programming mindset perspective. The bigger piece of information that loosely or strongly typed gives us is the idea of what kind of language is it from a performance perspective. Typically, loosely typed languages are also interpreted languages, which means that when they run, they're going through another computer program that is interpreting it to run locally on that computer's hardware. Whereas a strongly typed language is a mostly compiled language where we take it from the high level code like C, C++, we run it through this compiler before we run it. The compiler then converts that code into our assembly code, like we looked at Linux assembly. So right from the get-go, when you run a strongly typed compiled program, it is running natively on that hardware because you've compiled it before you're going to run it. Or an interpreted language is in real time translating for that hardware. Reality is computers are really, really, really fast. So 99.999% of the time, we're not going to notice. So really only is a problem when we look at that small percentage of, hey, I'm making a video game and now you have to think about how do I min-max my hardware? Maybe do something compiled because you're gaining the automatic speed that way. As opposed to if you're doing something which is actually kind of an interesting thing I just mentioned. I think I mentioned it last class with AI, is that most things with AI shouldn't lend themselves to a loosely typed interpreted language. But almost everybody who does anything with AI uses Python because that's where all the libraries are for it. Also, most of AI gets pushed off to the hardware, mostly graphics cards. So that abstraction layer of trying to translate between, hey, what talks directly to my computer's hardware versus just send it over to the GPU and let it handle it. Most of that speed is still maintained over in that side. But the world we're living in historically right now, or where I want your mindset to be, is this world where, hey, a long time ago we had the C programming language. It came out to write operating systems on early computers. That was the job of that program. And remember, early computers did not have very much memory, did not have that much processing power relative to today's stuff. So by necessity, also because the other ones didn't necessarily exist at the time, but by necessity, it was going to be a strongly typed language because that equals performance and lots and lots and lots of control over the exact amount of memory you want to use for something that used to be important that's starting to become important again. So it needed to be a strongly typed language. It probably needed to be a compiled language because you didn't have any extra processing power to do real-time interpretation while the program's running. So that kind of led us down that path. Now, so we were drawing this thing. We talked about some history stuff where, we had the C programming language, which is a procedural language, didn't give you a lot of tools for organizing your code into little pods and stuff like that, so your code could look messy, even though you could accomplish everything you can accomplish in an object-oriented language. But the upgrade to C was C++, let's say, because it gave us more control over organizing our code. The upgrade to C++ was maybe something like Java or C#, which just cleaned up some of the things that were a little bit less user-friendly. If you want to think about this in video game terms, you can further down this list you get, the more quality of life features have been added to the language, making your life just a little simpler. And now with AI, you almost don't write the code yourself anymore. We'll see plenty of examples, but we'll talk about the downsides to that. Okay, so that's what got us to this slide. All right, so when we're talking about primitive data types, what we're talking about is the kinds of values that the language allows us to store right out of the box. This is built into the language. There are other things that could be stored in that language that are built in terms of these things, but these are what's actually built into most languages, some subset of these. All right. So we started looking at these first four near the end of class last time. So we have a byte, which holds signed integers, signed being positive and negative numbers. A short also holds signed numbers. An int holds signed numbers. A long holds signed numbers. We have four different ways of holding signed integers. So then the question would be, well, why do we have so many ways of doing this? A long time ago, memory was really, really expensive. So if you only needed to use 8 bits, you should only use 8 bits. Okay, and what's the range of values that will fit in an 8-bit number? Remind me? 256. So negative 127 to positive 128 is 256 unique numbers that could be represented in 8-bit signed. Go ahead. Actually, we're talking about it in C right now. Most of these things should be true in Python, although Python does not have a byte or a short data type, but its integer data type is 32 bits. And these aren't things for you to like memorize. I mean, because when I say it's 256 unique values in a byte, that's 2 to the 8th power. That's what that number is. If we're asking about a short, which is 16 bits, it's 2 to the 16th power. Is the total number of unique values that could be represented with 16 bits. And if we want to hold a signed number, positive and negative, we need to have some way of storing the positive or negative sign, right? So that means we only actually get 15 of those 16 bits. All right, so for 2 to the 16th power is 65,536, but the range of values that fit in there are negative 32,767 to positive 32,768, if we're going to hold it as a signed value. There's still 65,536 unique numbers in that collection, right? If we decided we didn't want it to hold a signed value, which is possible, in fact, we see that with our chars, then we can still have 65,536 unique values, but maybe we start from 0 and go to 65,535. We're still using 16 bits to do that. We're just deciding, do I hold a bunch of negative numbers and a bunch of positive numbers, or do I keep everything in the positive side? I guess technically you can keep everything on the negative side too and just assume there's a negative sign in front of every value. But anyway you cut it, we're talking about bits in terms of storing things. What kind of things can we do with bits? All right, so short can hold 16-bit values, and int, which is probably our bread and butter. Most of the time you're writing C and C++ code, Java code, C# code. If you need to hold a whole number, you're probably putting it in an int. If you're counting from 1 to 10, the only numbers you're storing are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Do those numbers all fit within the window as negative 127 to positive 128? Yeah, they all fit in that window. But modern programmers wouldn't worry about that. We wouldn't say, hey, I only need a byte to hold this if I'm going to be a good steward of our memory. We would still say, hey, I have 128 gigs of RAM on my computer. I'm not going to spend very much time thinking about this. I'm going to put it in an int. If it yells at me that it won't fit, I'll put it in a long. And then if it yells at me, that won't fit, then I'll put it in a larger value. Go ahead.
So about the storage of negative and positive numbers, is one of the numbers in binary like for positive or negative, or does it actually have the negative and positive numbers separate? So is it really
No, it's all in binary. So here, I won't go too deep into this because this is really a computer organization thing. How do we store negative numbers? So the way that's going to make the most sense to you, well, okay, let's start with this. When I said a byte holds negative 127 to positive 128. This is 256 unique values. Okay, we agree with that? The negative 127, where's the 127 values over there, plus a 0, plus 128 values over there, gives us 256 total values. All right, so he's asking, well, how do we actually store the negative? So all these values here, so a positive 128 is 3, 4, 5, is that. This is positive 128. Going into that too deep. That's negative 127. All right. The easiest way for us to understand this or think about this right now without getting into something called two's complement, which is how negative numbers are actually encoded, is to just say, we're going to take the far left number here, the far left bit, and we're just going to say that bit is no longer used for magnitude. It's no longer used for a value. It's only used to keep track of positive or negative. Make sense? All right. So there is one problem with that that makes it a little bit less efficient. That is why we don't actually do it that way. We actually do it using something called two's complement. Can anybody recognize in here why this is using just that far left bit is technically not as efficient as it could be when storing negative numbers? Go ahead.
Just because like when you're trying to, best way to do that is when you have that last value that's included, it would kind of like off balance the counting, if that makes sense. Like that in itself, the first 128 is 128. But if I add that one and I'm trying to get like 129 or something, now I have to represent that in it's confusing. I don't know.
What are those two values? Would you guess based on having a bunch of zeros and me telling you that the far left thing is a positive or negative?
negative 0 and positive 0?
Negative 0 and positive 0. Do we need to have two ways of storing 0? That seems barely inefficient, right? Like, look, we got 256 values. I'm going to use 255 of them. That seems good enough. Well, not in computer speak. In computer speak, it's inefficient to store 0 as a positive and a negative number. So that's why we get the extra value on one of the ends, negative 127 to positive 128. So we are only storing 0 one time, and we're gaining one extra unique value out of it. But that gets into how does two's complement works, which we're not going to talk about in here. That's a computer architecture thing from next semester. You go through, you flip all the bits, all the zeros become ones, all ones become zeros. You add 1 to it. That's encoded in two's complement. Leave it at that for now. And it's not hard to do, but it's a little bit difficult to explain. All right. So, but when we talk about something being an 8-bit number or 16-bit number or a 13-bit number, what we're really talking about is how many zeros and ones do I have to work with here in order to represent the values I'm interested in representing. With a byte, we have 8 of those. With a short, we have 16 of those. With an int, we have 32 of those. With a long, we have 64 of those. With a long, we have 128 of those. If you're in a C++ or newer, they disappeared actually in C# and Java because they moved over to an object type. But bottom line is you can store arbitrarily large values in any of our modern programming languages. If it doesn't fit in one of our primitive types, there will be an object type that lets you hold bigger values at the cost of performance. So you're not going to run out of space. It's more of just what's the right tool for the job. You're probably not going to get one of those gigantic, tractors that mow farmland if you're only mowing your apartment's backyard, right? You work with something a lot smaller than that. All right. So we have 4 different ways of holding whole signed integers, and that's because we mentioned the Y2K issue. Memory used to be really, really, really expensive. We didn't have a whole lot of it. So an old school programmer would have had to pay a lot of attention into, hey, I need to hold a positive or negative whole number, but let's make sure we're holding it in the smallest memory footprint as possible. That's not the world we live in today as a computing person. So now we get to chars. A char is also an 8-bit value. Now, first of all, we've said this a couple times before, is that humans we're okay with numbers, but we like letters and other things that we have our language. We're not purely zeros and ones. Computers like numbers. So whenever you're trying to think about, we're trying to understand this guy so we can tell him what to do. At the end of the day, everything that we do on our side is gonna translate into a number on this guy. All right. So all these things we're talking about here is how do we map something that makes some sense to us to something that will make sense to him. All right. So a char is an 8-bit. This is in C is 8-bit if it's newer than C. So Java, it uses Unicode, so it's 16 bits. But it's a unsigned integer, which means it'll go from an 8-bit unsigned integer uses all 8 bits for a positive value. So that gets us a range of values between 0 and 255. We still have 256 unique values. There isn't any more extra unique values there than we had with a signed number. A signed number let us go negative 127 to positive 128. An unsigned 8-bit number lets us do 0 to 255. We just dropped the ability to keep track of positive and negatives, and we gained the larger positive side. We can go up into the 200s. Why do we only need unsigned numbers for this? Because we happen to be using the char primitive type to map to a character set. ASCII for older languages, Unicode for modern languages. What's a character set? A character set is a giant chart they made that has all of the symbols and letters used in various human languages. ASCII was basically just English. Unicode incorporates other languages from around the world, but any symbol that you might write in any, or let's say most languages, will be somewhere on the Unicode chart. Every symbol you might write with English will be at the very beginning of the Unicode chart. The first 256 buckets of Unicode are identical to ASCII. So we can say Unicode is a superset of ASCII. All right, so the first 256 things in Unicode are the same as all the 256 things in ASCII. Go ahead.
So does signed always mean numerical and unsigned always mean grammatical?
Yeah, when we say signed or unsigned, we are literally talking about whether we can store negative numbers. We're still using the same number of bits. We just happen to take one out of the equation for storing a larger value because we're going to keep track of positive or negative with one of those bits.
Okay.
But yeah, 100% of the time when you see signed or unsigned, we're just talking about negative numbers or not being able to have negative numbers. All right. And I think last class, we looked up somewhere and somewhere I took a letter and I showed you how that letter, like a letter H or something, how that's represented in binary from the ASCII chart. So if I go ASCIItable.com, Here's a capital A. A capital A is the decimal value 65. All right, this guy right here. So an A is decimal 65. And if I were to ask you, well, what is the binary version of an A? Now we know, since we just got that off ASCII, it's going to be an 8-bit value, right? There will not be an ASCII value 265. Why not? Largest ASCII value is 255, right? 265 does not fit in 8 bits. It requires 9 bits. All right, so decimal 65, this is going to be our pattern of how do we take a decimal number and convert it to a binary number. So this is our pattern where we divide by the base over and over again, record the remainder. So 65 divided by 2 is 32. 32 times 2 is 64, so we have a remainder of 1. 32 divided by 2 is 16. Remainder 0. 16 divided by 2 is 8. Remainder 0. 8 divided by 2 is 4. Remainder 0. 4 divided by 2 is 2. Remainder 0. 2 divided by 2 is 1. Remainder 0. 1 divided by 2 is 0. Remainder 1. Of course, I picked that one. So we read it from bottom up, even though in this particular example, bottom up is the same thing as bottom is top down. But this is the first one we write. So it's 1, 0, 0, 0, 0, 0, 1. So that is 7 zeros and ones, which means we put an extra 0 at the beginning of it to get us to 8 bits, a byte. And just to give you the idea of padding, if I have the number 1 that I'm representing in binary, so decimal 1 is equal to 1 in binary. Makes reasonable sense, but that's the same number. 7 zeros followed by a 1 is also 1 in binary. Our smallest footprint in all of our modern languages are bytes. So we have 8 bits is the smallest number of bits we can work with in a modern programming language. There's actually something that's half of a byte. Anybody know what a half of a byte is called? Nibble? It's called a nibble. Nibble. That's half a byte, 4 bits. Which means that, remember our trick for hexadecimal? We can represent every hextet using 4 bits. So that means each thing is a nibble. Nobody actually uses that anymore. We just think about everything in bytes and whatever. All right. But the punchline here, the reason I spent some time looking at this is this number right here and this number right here are the identical number. But if we want to visualize how is the number 1 actually being stored across 8 bits, all of those 8 bits are used. We have 7 zeros followed by a single 1. Right? That's important if, for example, we had a message. Before long, when we start writing some real code, we'll write something where I'll have like a sentence. And we will make that sentence be the binary version of every single character that's in that sentence. So we'll just see a wall of zeros and ones. And then we'll say, oh, well, let's write a program that converts this back to English, something we understand. Now, if we didn't represent every single character as the full 8 bits, we wouldn't know where each character begins and ends. If we just threw the number, a single bit in there to represent a 1 at some point for whatever the first value is in the number 1 is in ASCII, we wouldn't be able to consistently convert it. We need every single individual character to be represented fully with 8 zeros and 1s, even if just about every single one of them is a 0. Does that make sense? Because that's the first 8 bits is be one character. The next 8 bits is the next character. The next 8 bits is the next character, so on and so forth. So I need to use the entire bit space. All right. Which is why I would say you would rarely ever see someone write 1 in binary that way. You would always expand it out to the number of bits, and almost always it would be written as a byte. All right. All right, so that's our signed integers and our chars. Floats and doubles are both decimal point values. We can think of a float as kind of like the int version of a floating point value. And a double is like the long version of a floating point value. So a float is 32 bits followed by a decimal point followed by 16 bits for a total of 48 bits. All right, so if we are writing a floating point number like 3.14, that number would be represented with, so the number 3 is, good.
Said that 32 bits, it's 32 bits and 16 bits. That'll be like, what is that? 32 bits, period, 16 bits.
That means that you have a whole bunch of zeros or a whole bunch of zeros and ones. Let's just assume I have 32 of those, followed by a dot, followed by 16 zeros and ones. That is the number that makes up a floating point value.
The decimal point.
Just hard coded, just in the system, it's assumed that there will be a decimal point. We don't store it. Yeah, we're not storing the decimal point in the value. We just know that the first 16 bits are the point before, or the value before the decimal point. And after, in the next, well, the first 32 bits for a float, the next 16 bits are the number after the decimal point. So for example, if we had, let's just do it on another slide. 3.14 as a float. Well, we need to first convert to 3 to binary, which is 1, 1. This is the 1's place, this is the 2's place. 2 plus 1 is 3. Then I need to put 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 26, 27, 28, 29, 30. So we have 30 zeros before the 1, 1. Then we have our dot. Then we need to get the number 14. So we have the 1's place, the 2's place, the 4's place, the 8's place. So we would have 8 plus 4 is 12 plus 1 is 13. So 1101. So that is a 14. Actually, I said that's 13. That's a 14. But this is supposed to be 16 bits. So I need to put now 12 zeros before this guy. That is 3.14 as a float. Make sense? And 3.14 as a double would be an additional 32 zeros before this guy and an additional 16 zeros before this guy. Otherwise, it's still holding 3.14, it's just holding it in a larger container. All right, that makes some sense? So a double is 64 bits, followed by a dot, followed by 32 bits, or 96 total bits. So this is, we could think of this number of bits as kind of like how much do these values weigh? Regardless of what value it's holding, if it is being stored in the format of a double, it will always weigh 96 bits. Even if a majority of those bits might be zeros if you're dealing with very small numbers. Make sense? Okay. Now this stuff is actually important to understand, not important to memorize. Like I'm not going to ask you on a test like, okay, well, how many values after the decimal point, how many bits after the decimal point does a double have? You don't have to memorize that, but understand structurally how floating points and double values work. We have some number of bits before the dot, some number of bits after the dot. Those two things together give us the magnitude and the precision that comes after it. For integer types, we don't have dots. We just have whole numbers. So we don't have to worry about precision, but we get everything as magnitude. A Boolean, this is a true or a false, typically represented as a 0 or a 1, but most modern languages, as I mentioned, hold these as bytes, 8 bits. So we have 8 zeros or a 7 zeros followed by a 1. Those are our two binary values. Some of our modern languages might actually represent, in fact, it seems like they do represent them this way, or at the very least protect it in this way. For instance, Java, a true and a false might just be hard-coded into the language. But at the very least, they protect it so you can't do math with these. Whereas in an older language like C and C++, you technically could take a value that is a Boolean true and add 4 to it. That's a thing. Because technically, these are just numbers. If I give you a number and I say add 4 to this, you could add 4 to any number, right? Even though a Boolean true doesn't have a numerical meaning. We're just using the number to represent what true is to us. Does that make sense? So just because you could do math with it doesn't mean you ever should do math with it. Very similar to what we said earlier, just because you can in a loosely typed language, just because you could change the kind of value you're going to put in a variable, doesn't mean you really ever should do that. You probably are going to have a variable that has a meaningful name for the kind of value you're going to store in there, and that name likely would not be meaningful anymore if you were storing a entirely different type of value in there. All right, if I have a variable named age, it would never make sense for me to put Mike in there. In a loosely typed language, I could, but it never really makes sense to do that. All right. So these are our primitive types. Basically, what do we have? Whole sign numbers, characters, floating point values, signed, and Booleans. That's it. Those are the kinds of values built into all of our programming languages. All right. All right, we did our mappings for hex. Okay, so we had looked at various conversions. We looked at our two patterns for going from decimal to any other base or from any base to decimal. We've improved it to ourselves by going from decimal to decimal. We can use the same pattern. We can use both patterns to go from decimal to decimal. The pattern is depending on which side of the equation decimal's on. Do I either do the divide thing with the remainders, or do I do this is the ones place, the whatever's place? If you're converting decimal to decimal, they both work. But we asked the question, what is hexadecimal for? Well, hexadecimal we know is base 16. Okay, so what are the legal hextets in hexadecimal? Every hexadecimal number you ever put in front of you will be made up of what characters? What are the possible characters that can live inside of a hexadecimal number? A through F and? What comes before the A through F? 0 to 9. 0 to 9. So we have 0 to 9. And then we have A through F. Why isn't there a 10? Why do we use A for 10 instead of just the number 10? Yeah, 10 takes up too much space. It's like having to buy an extra seat on the airplane. Speaking of which, Southwest, nothing. I know I seem petite, but in real life, I'm actually quite large. And so when my wife and I travel quite a bit, and we usually will fly first class United, where I just pay for a bigger seat and stuff. I'd rather fly that because you get an open bar. I make money on that one. Although I lose on the backside because my wife doesn't drink at all. Huh? Yeah, yeah. So, anyways, Southwest, not that they should ever have to do this, but Southwest has a passenger of size policy. How many of you have ever flown Southwest? So you have to go and get in the cattle call, right? And then compete for seats. You know what I'm talking about? Okay. No, I don't have to do that. They give me an extra seat for free. And they give me a pre-board. So I get on with the wheelchair people. I'm just sitting there. I already got my VR headset. I'm already watching movies with an extra seat in between us. I got my little seat reserve sign there. People are just walking by all ticked off. Oh, it's great. It's really empowering. Now, they should never have to do that. If you're too fat to fit in one seat, you should buy two seats. Or, I prefer to just fly first class and then I have the bigger seat. But yeah, they're taking that away, but in two stages. Now they make me pre-buy my second seat, which is fine because they guarantee the refund after the flight. But starting next year, you're rolling the dice. Starting next year, you have to pre-buy your extra seat, and you only get refunded if the flight happened to fly with at least one empty seat on it. So you don't know if you're going to get refunded or not. And they're getting rid of their 2 free bags. Everything that made Southwest good is gone. Now they're just a normal airline. They're fine. I don't dislike Southwest, but I let them go first. It's like, move it, Pops. God.
Can you express that problem in Python?
Oh, the pat, and actually, it's not just a fat thing. It's shoulder width. So, I'm not just, I'm a big guy. So, and what's funny though is my wife and I do take up exactly 2 seats though, because I have a pocket wife. She's she's 5'4", 100, and when we got married, she was 105 pounds. Now she's a little heftier, but a lot of donuts in those years. We've been married 25 years. I'm allowed to say that. All right. So what were we talking about? Oh, hexadecimal. So I don't know how I got off on that other thing, but that happens. So hexadecimal. All of our values are made up of the numbers 0 through 9, the digits 0 through 9, or A through F. Why do we use an A instead of a 10? Because a 10 takes up 2 seats, 2 spots. And that would no longer make sense for us for writing out a value because we wouldn't know, did you mean 1 followed by a 0 or did you mean 10? So now we just do it with an A. This means 10. Whenever you do math with this guy, pretend like the A is a 10. Whenever you do math with a B, pretend like it's an 11. If you have a remainder of 11, when you write your final answer out, turn it into a B for display purposes. Make sense? All right. Decimal, 0 to 9 are our digits. Octal, 0 to 7. Octal's base 8. So the values, the kinds of values that make up a number in any base is 0 to that base minus 1. And anything after a 9 starts using the alphabet.
Wait, what was that you said -1?
Like for instance, decimal is base 10. The legal values are 0 to 9. So if n is 10, the legal digits are 0 to n minus 1.
In base 16 is like if I have 16 and then to the power of something like 1, 2, 3, 4. That's how we represent that in binary.
Ask that again.
Like when we're dealing with regular bits and bytes,
Mhm.
we have like 2 to the power of 1, 2 to the power of 2, 3, 4, 5, so on. We're representing them in bits. Like
Well, that we're representing that as base 2. At the end of the day, all these are represented as bits in a computer
yeah, no, but base 16 is pretty much just switching the 2
to a 16. Yep,
Okay.
100%.
Yeah.
As well as every single other base. Base 24 would be 0 through 9, A through whatever the uh, uh, 14th character of the alphabet is. Sing the song in your head.
So not. Because 0 through 9 is basically 1 through 10, if we think about it.
Well, yeah, but I mean, we don't use 10 because it's two buckets wide. It's too big to fit into a single spot. So we are not going to be able to tell the difference between a 1 followed by a 0 and the number 10.
Yeah.
We don't know which of those is, and if we don't know, the computer's not going to know. All right, so what is hexadecimal for? So we have these values. And so for example, if I had the value 2989 in decimal, now I'm going to tell you what this number is in hexadecimal. That's bad in hex. And let me just cheat real quick here. We can do the math if you really want to.
Let's see what it means.
We can go back and do the math. I taught you how to do the math. All right. So all three of these values are the same value. They all mean the same value. They're just expressed in 3 different languages. One is in the language of binary, base 2. One is the language of decimal, base 10. One is the language of hexadecimal, base 16. But they all mean the same thing. What's your observation of hex versus binary? What's the difference between those two values? What stands out right off the bat?
The less the word.
Yeah, space. Space. This is only 3 characters long. This is a lot more than 3 characters long. I can count them, but again, I'll just cheat and say a lot more than 3 characters long. So when would we use hex? We're getting back to this idea of, we already said that, okay, well, computers use decimal because humans are involved. We use binary because computers are involved, 0s and 1s, on and off. We use octal. Why do we use octal based on what you understand at this point? Exactly 3 bits. Every octet, every character that makes up every single octal number, 0 through 7, can be represented in exactly 3 bits. 000 is a 0, 111 is a 7. All right, so you can fully describe every single octet in exactly 3 bits. The fully described is important there. Hexadecimal, same thing, but we're at 4 bits, right? Every single hextet, 0 through 9, A through F, can be represented in exactly 4 bits. 0, 0, 0, 0 is a 0. 1, 1, 1, 1 is an F. That's 15. Make sense? All right. So that's why we specifically picked hexadecimal, because of that shortcut. If our values get even bigger, we would go to something that could be represented across 5 bits instead of 4. Okay, which would be a jump up into the base 20 something. All right. So now from a computer perspective, though, you'll see hexadecimal all over the place in the computer. For those of you, and I don't expect you to have this answer, but those of you who have done some programming before, when do you see hexadecimal numbers in a computer? Let me do something here. You can do it. Maybe. All right, here we go. So let me just write something in C here real quick. Oh, so if I say int pointer is the, let's call it address, is the address of age. I'm going to change this to IO stream. Actually, I'll leave it. I'll leave it to show you the old way of doing it. So this would be %D, then that. All right, so there's my 21. You can see that down there, small text. So I created a variable here, age. I said it's an integer, so this must be a strongly typed language. I'm describing the kind of value that it's built to hold, and I'm putting a number in there, 21. When I print out that guy, this %D is a placeholder for a decimal value. This is old C code. I'm printing out age, it prints out that 21. If I change the 21 to a 27, I run this again, it'll print out a 27. Now, I'm gonna go printf %P. I'll call that address, or you could just say &age. They mean the same thing.
I think you just forgot the semicolon.
That's fine. I did. I'll put it back to my variable anyways. All right. Let me kick it down a line here so we can see it better. Here, I'll kick it down a couple of lines. What does that guy right there look like to you? Here, we'll copy that and put it into our. Is this thing right here made up of 0 through 9s, A through Fs? Memory addresses is the primary place where we see hexadecimal used in a computer. So what does this code do? This creates a place in my computer's memory called age to hold the number 27. It's a variable. You've been messing with variables in Python. If you were writing this in Python, you would have just not said int, you would have just said age equals 27.
So it's more so to like store variables in a specific place in the computer.
Let me get to it. Give me 1 second. So this second variable, not that important. This is a type called int pointer. It's built for holding a memory address. That's what an int pointer is. I mentioned earlier that newer languages like Java and C# have some quality of life improvements. I don't understand this really, but beginning programmers get very intimidated by hexadecimal numbers. They scare the crap out of them. And so storing stuff in pointers starts becoming an intimidation thing where Java has said, hey, we're just going to take away the special syntax for pointers and we'll just handle it for you. We'll make sure things get sent the right way so that you don't have to think about memory, you buffoon. You know, they're basically saying you're too stupid to do it. So they're just taking away the syntax. But in this case, we're using the syntax and we're going to say, okay, address here, this variable named address is holding on to that little ampersand that's before age that says, give me the address where that variable lives in memory. I created a place in memory for that variable right there. I didn't get to choose where in memory it went. My operating system says, oh, you need to store an integer? How big are integers in C? 32 bits from our primitive type slide, right? We had There we go. So here's an int, 32-bit signed integer. So we know that this guy right here, we're asking the operating system, give me 32 bits of memory somewhere on the computer. Just someplace it's not being used by somebody else. So it's going to go out, it's going to find that for us magically. It's going to come back and say, okay, I found the perfect spot for you. I went ahead and put the 27 there. Got it tucked away for you, no problem. So then later on, when I said, okay, go ahead and, I need the value of age again. So go look it up there and resolve age to be the value that you've held at that memory address. But now, as interested computer programmers, we might say, okay, I'm actually interested in what address specifically they put age at, because I didn't have any play in it. It didn't matter which address they put it, but let's just find out what it was. So I said, okay, I'm going to create another variable called address. And being a strongly typed language, we have to specify the kind of value we're going to store there. And we've said, oh, this is going to be an int asterisk, which is an int pointer. Whenever you hear the word pointer in computer programming, think memory address. So this thing is capable of holding an int memory address. What's the difference between an int memory address, an int pointer, and a char pointer, for example, or a long pointer? No. Well, for char, we'll probably use the bad example. Positive or negative would be a true statement. So let's just say int versus long. What's the difference between a int pointer and a long pointer? How big the value is. So if I ask the operating system to store an integer, it's going to go out and find me a plot of land big enough to hold 32 bits. But if I say I'm going to hold a long, so if I say long age 2 is equal to 27, I'm storing the exact same value there, right? But now it's storing it as 64 bits. So that means when I asked the operating system to give me a place big enough to hold a long, it's going to go out and find me a plot of land 64 bits big. We wanted a big backyard, when you're hunting for this real estate. All right. Now the memory address. So if I let's play this out. So if I stick that, and I say ampersand age 2, we run this guy. Oh, let me kick it down the line because it's putting them right next to each other. I don't have a carriage return in there. Notice that these two memory addresses are right next to each other. Actually, this is a fun one since they run us in our own virtual machine here. So this was the memory address of our int age. This was the memory address of our long age 2. Aren't these addresses the exact same size? Why are they the same size if an int is 32 bits and a long is 64 bits?
You're still storing the same value. So
Yeah.
you're like, they're right next to each other.
Well, if I go out and buy land, let's say I buy an acre of land, I could put a giant house on that, or I could put a little shed, right? I still have more land, but this is just telling me what my street address is. Where can you find that land? This doesn't tell you about what's actually built on that land, what's actually stored there. Okay, so this guy right here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that is 12 hextets, which are 4 bits. So that means that memory addresses here is a 48-bit memory address. So we're working backwards here. So I'm going off of online GDB, this website, and whatever operating system they're using is producing memory addresses that are 48 bits long. Now, let's keep, I'm still going down this thing. So right now, all these things should be floating around up there, all these bits and bytes and 48 this and 64 that and 32 that and 8 and 16 and all this stuff. But I want to connect them to things that you've seen around, just like with your cable modems and stuff. We talked about internet speed. So how many of you are console gamers? How many of you also like older gaming systems? Okay. So original Nintendo. How many bits was original Nintendo? It was a 8-bit gaming console. Okay, what about Super Nintendo? 16-bit. What came next? Nintendo 64? Was there another guy in the middle there? Now let's just jump, doesn't matter. Nintendo 64 was how many bits? 64 bits. Yada, 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 yada. What does it mean to be 8 bits or 16 bits or 64 bits when we're talking about a video game system? We all know about bits in here, right? We've been talking about bits a lot. And we've also been kind of talking about bits in the context of, oh, well, they're just a bunch of zeros and ones that we use to represent something. Not always a number, not always something you're going to do math with. So what might 8 bits for the original Nintendo be representing for its, what might that be talking about relative to that Nintendo?
Like quality per se,
Okay, what aspect of quality would you guess?
just like things.
Let's go clearer than things. Which things? Okay, what about graphics? What goes into the quality of graphics? When we think about graphics, what are the things that we care about with graphics? Okay, image quality, color quality. What are the measurements when we think about image quality? What's the measurement we use? We use resolution. Okay, what about color quality? What does it mean for color to be higher quality than another color?
It's like it's less like,
More colors,
yeah.
right? You know, I remember back when I was in, do they still have the 64 crayon box that comes with the sharpener?
Yeah.
Oh man, you were the coolest kid in elementary school if you had that. But then I had an incident where I ate crayons. Man, I got spanked in first grade for that. I ate half that box.
Ooh.
Go ahead.
Spreadsheet because they only use for amount of colors and like older Nintendos are like
Mhm.
8-bit one, they only have 8-bit colors. They're like, there's a way less colors.
So there's a combination here. When we're talking about video game systems, we have two things at work here. We have the resolution of the system. So if we go back to the Nintendo days, Nintendo, when you played the game, it showed up on what screen? TV set, right? What was the resolution of TV? And oh, when did Nintendo come out? 87? Late 80s. Let's just go that. Mid 80s, mid to late 80s, mid to late 80s. What was the resolution of TV, do you think, back then?
480.
Yeah, 480p. Actually, it was back then it was 480i. So this was 640 by 480. Now, when I say 640 by 480, what am I actually talking about there? 640 what? By 480 what? Pixels. Pixels. So that means that that's 307, 200, 307. So we have 307,200 total pixels that make up a single frame on a TV back then. All right. Now, when you're playing a video game, it's like one of those flip books, right? You know, when you are playing your games, those of you who are gamers, when somebody says, "Oh, what's your FPS?" What are they talking about? Frames per second. What does that mean? Yeah. How many pictures are we showing you per second to trick your eye into thinking this is video? This is pure motion, right? All right. So usually TV is 24 frames a second, something like that. At least that's what it is for the movies. You know, that probably would not be good enough for if you ever, you know, when you go to you're shopping for the big screen TV for the Super Bowl or something like that. And, you know, they say, oh, well, you know, you're really going to want the 240 hertz TV, you know, instead of the 120 hertz TV, right? You've seen those advertised. What's the difference between 120 hertz and 240 hertz? Refresh rate. Well, what is refresh rate? How many pictures is that TV capable of showing every second? 120 hertz can show 120 pictures, 4K pictures on a modern TV, let's say, every single second. But 240 hertz can show 240 pictures in a second. Well, isn't 240 better than 120? So now this becomes very interesting with gaming. Anybody in here on the esports team? We have a coding 1 class with no esports players. It's like the sign of the apocalypse. Okay. So imagine, if you will, you have somebody who's you know, a high-end Call of Duty player or something like that. Now, their monitor is capable of 240 hertz, let's say. Most gaming monitors will be that. Their graphics card, or if it's their you know, Xbox or PlayStation, is probably going to try to stick to 60 frames per second, right? That you want to maintain 60 frames per second. Now, if you are playing on a PC instead of your Xbox or whatever, that has a super high-end graphics card that could produce more frames per second than that. Let's say it can produce 240 frames a second. If it produced 250 frames a second, would you be able to see all 250 frames? Well, the monitor can only show 240 of them, right, in a second. But let's just assume we're showing all 240 frames. You got a high-end graphics card, you can keep up, yada, yada, yada. And that's a pretty high frames per second to maintain. But would well, first of all, I'll tell you this. The human eye can see something like 42 to 48 frames a second. That's what we're physiologically capable of seeing according to the scientists, right? But if you're talking to one of these people who's used to playing these real-time games, they can tell the difference between 40 frames a second and 200 frames a second. There is a perceived smoothness that exists, even though the eye is technically not capable of seeing it. Okay? We just went back and described how AI works. We've trained ourselves to notice the pattern of smoothness, even though our eye can only see so many pictures at a time. And you've even seen this back at old movies. Have you ever seen an old movie that had a TV screen in the back and you saw the lines going down the screen? You don't see that in real life, do you? Yeah, you do. You just don't notice. You know, when I started using computers way back when, we had CRTs, TV set looking things. So I was sitting in front of these things for hours and hours and hours every single day. My eyes were having to deal with that refresh rate. And I basically blew out my focusing muscles in my eyes. So I wore trifocals starting as like a 14-year-old because I was staring at screens that were forcing my eyes to do, you know, to see that even though I wouldn't have seen it. You know, I didn't perceive I saw it. Now we have active matrix screens where that refresh rate 240 times a second is pretty fast. You probably wouldn't see that you might see a little flicker if you see it on a video, you might see a flicker on the screen or something. But anyways, so we're starting to see how all these things kind of mesh together. Okay, we have so many things that are related to each other we just take for granted, but we don't really know what they mean. All right. So when we talk about Nintendo being an 8-bit gaming system, and it was designed to run on TV sets running at, this is called 480, 480i resolution, 480 interlaced. So 640 pixels wide by 480 pixels tall. What is those 8 bits? The 8 bits is the number of bits that we have to represent the color of each of those pixels, which means that each pixel on Nintendo could be one of 256 unique colors. So in that case, they're using the 8 bits to represent colors. The more colors you have to choose from, the higher fidelity graphics you're going to have. If you have 16-bit colors, like you do on, because they actually deviated from colors later on, but if you had 16-bit colors, now you can represent 65,536 unique colors. That's a lot more colors, right? So you have all these shades of red and stuff like that. So you can get to these higher quality textures. But then as our TVs went from, 480p to 1080p, 1920 by 1080 pixels, normal high definition, right? Now all of a sudden we had more pixels to work with, and we had to kind of take a step back and say, okay, well, do we really need more than 65,536 colors? I mean, maybe 256 colors was a little bit plain, but do we need more than 65,500? At some point, the human eye is not going to be able to tell the difference between 700 shades of red, right? So, but now we have more pixels to cover, so we're going to use some of those bits for those things. Okay, but at the end of the day, we're just using bits to hold stuff, and we get to decide what are we putting into those bits. Make some sense? Okay, so whenever something says, "Oh, this is a 64-bit processor," or "This is a 32-bit," this, that, and the next thing, those bits are representing something about that technology. And where we got onto this conversation was when I wrote down our memory thing. Man, these notes have to be impossible for you to follow since I don't know where I'm putting crap. Yeah, well, it's not my problem. Thank God. Jeez. Where is my 48 bits one? What? All right, hold on. We're just gonna take that again, and we'll just make that slide again. So you'll find it somewhere else in there.
I think it's past.
I passed it.
Put it right there.
No.
4-bit values.
It should be right in this area here.
Do command.
Oh, is this it? Oh, here it is. Thank you. So up top here, we went through and counted these, and we said these memory addresses are 48 bits. That means that online GDB, that website that's letting me write code, that's running on top of an operating system, probably Linux, would be my guess. And that 48 bits tells us some information about its memory management system. So when you take the operating systems class and you start learning about all the different things that an operating system does, process management, memory management, amongst other things, driver management. So memory management says, hey, I'm going to keep track of where everybody's memory addresses are. That's the guy that handed us these memory addresses. All right, that memory manager. And the memory manager happened to hand us a 48-bit memory address. Now that number tells us something about how many bits the memory management system is on that probably version of Linux. So what's the number of bits the memory management system on that version of Linux has? You're going to guess 48. The answer is 64. Why 64? Modern 64-bit OSs, the memory manager, 48 bits, user, accessible, memory space. Yeah. 16 bits, is super user, OS level, yeah. Reserved for OS and super user, admin. So we still have our 64 total bits. We just say 16 of these, so 0 to 65,535. Those first, 65,536 addresses are reserved for the operating system. Everything after that is reserved for users to do whatever they want with. All right. So, did I lose it again? I did. This is terrible. All right. So we look at these two numbers. It ends, so everything leading up to the end is the same number. So we have, this is a 54. Remember, this was an integer age. And this was a 58. What's the difference between the 54 and the 58? It's 4, right? 4 what? 4 bytes, 32 bits. How big's an int? 32 bits. So what did we see here? We saw that right here, I'm asking the operating system, give me 32 bits of memory. It went out and found its 32 bits of memory somewhere. Immediately following that, we went out and asked the operating system, give me 64 bits of memory. 8 bytes. Went out and found those somewhere. If I then create another one and I say int age 3 is equal to whatever, and then I print out age 3, I'm not going to quite do this yet because I'm going to have you tell me. So to go from my integer age to age 2, we saw a jump of 4 bytes, which means that this number right here is the beginning of my number, the beginning of my 32 bits that represent an integer. That's at the very beginning of it. So now you fast forward 32 bits. Now where are you at? You're at the beginning of the next number. The beginning of the next number is a long, just because we happen to see that it handed us those addresses right next to each other. We're seeing the results of the memory manager handing us results. So if I'm now putting an int after that, what should the next address be? How much farther away from the second address to the third address be? 8 bytes. All right. I'll run this again. We have D90, D98. That's my long, although hold on. So, something else did take up space in there. D94, oh, that's interesting. So it actually handed them the addresses out. There's no guarantee they live right next to each other. Each time we're asking the operating system to give us the address. So this is our first number. It's at 90. That's an int. Here's our second int at 94. And here's our long at 98. The thing that would come after the long would be the next value up 8 bytes away. All right. Next assignment is up. I think it's due Saturday again, whatever. So keep working on that. Next time we're going to come back and we're going to start talking about Boolean expressions. Then if statements, then loops, and then we'll start writing some real stuff.
Yeah, it's not. Are you planning on doing that? Okay.